Hi. So it's been a while since I've uploaded a video to this channel. Um, yeah, it's been like 2 weeks or something. It's like been crazy. I've been somewhat busy lately, so I haven't had the time. I wanted to show off something interesting. I've worked on a new like Desmos 3D graphing calculator. Desmos released this like I think somewhat. It wasn't like too. It wasn't like super recently, but it was some time ago. It's in like beta, I think. Like they're like making like open for anyone to use. Yeah, I'm messing around with it. I made this interesting model of 3D how like 3D graphics work with respect to an observer looking at like a cube. So here we have the cube right here, and this is the observer, and this right here is what the observer sees, and like this arrow, this purple like arrow here, that's like a vector, represents the direction they're looking in. So as you can see here, it's red, just the red square. It's because the observer can only see the side of the face of the cube. It's red, obviously. What they see is red. They're going to see red, right? Makes sense. Yeah, I would be surprised if they saw blue or something. It wouldn't really make much sense. So I'm going to take this cube. I can actually rotate it. I'll show you what that looks like. Let me go back just a little bit. See, if I turn an angle, now the observer can actually see this. Hold on, let me turn to the other side. Both this black face and this red face here. And of course, like behind it, there's a green face and like another. I think it's an orange. I think. Oh, no, orange is underneath. What's the one over here? Let's check that. Let's see. Sorry, it's like really slow. Unfortunately, like Desmos slows down a lot when you are recording. Blue. That's what it is. Okay, so I'm gonna turn. I think it's this one. I think. Yeah, there we go. You can see. Oops. And now we have a 3-point perspective projection. So that there's vanishing point this way, vanishing point here, and maybe vanishing point down here. So you can see we can see the purple and the red face. And this is interesting because normally when you make a perspective projection, it wouldn't look like this, and you'd actually see all the faces at once. It's like let me show you what that looks like. If I go down here, where is that? So there's the cube right there. That's going to disappear. Right. This is what it normally would look like. I'm sure you can see it very well. Let me zoom in a bit more. So you can see, right, there's the cube, and like you can see all the faces at once. But what I figured out is how to hide the faces, like the faces that are obstructed from the view of the observer. So like this blue face and like the green face and this orange face over on the back, the observer can't see it anymore, unlike before where you could see all the faces at once. Of course, this doesn't make any sense in real life because when you look at like a cube, right, you're not able to see all the faces at once. You're only able to see like certain faces. So I want to turn around so you can see. Look at it from different angles. Show you what this looks like. Sorry it's a bit snappy because I'm trying to turn it, but it's really slow, unfortunately. Okay, let me go back up. Actually, no, let me actually disable the right there. Disappear. Actually, I guess I could overlay the faces with the lines just to show you what it looks like. Yeah, so you can see this red face corresponds to this part. Black is here, and this would be the what was this? I think this is the green face. Yeah, this one right here, and the purple face is this one here. So some of you are probably wondering, how do you get this to work? How did I get this to work? Like, keep in mind this is all just like math and stuff. How did you get like all this to work? Like how is like Desmos know what faces to show, what faces to hide? Well, it's actually surprisingly not actually that complicated. Like, surprisingly, it's not. I do want to show some other things first before I go into how it works. So, like, for starters, you can take the observer, and you can actually make them like change the direction they're looking in. or their position space. Like for example, I can move the observer on the y-axis, and you can see the image would change with respect to their position. So now I can't see the red face anymore because the observer is over here, and they're only looking at this side of the cube now. I'm gonna turn my or change your perspective here. There we go. Because now here's the, and keep in mind this is not actually a 3D thing you're seeing here. It's actually just a 2D image, as I already said. But I just want to clarify that for anyone who's confused. This isn't actually. It looks 3D, but it's not actually 3D. I guess to move the observer up as well. I think you should see the green face if I move up high enough. Yeah, you can see it like right there. Of course, it gets distorted because you can go far away, and it's outside of the. Normally, you wouldn't like your field of view would only be so large, so you wouldn't normally be able to see that far around you. That's why it looks distorted and weird when you go far away from it. It's supposed to look like that. Okay, right. 0. This will change the observer's direction, the viewing direction, so we can turn this. And the observer's looking this way, like this way, instead of this way anymore. We can also make them look up. Like this. You're probably wondering, like, okay, what if I made the observer go through the cube? What happens is that this will get bigger. The image gets bigger because you get closer to the object. It appears larger and larger, just like in real life. Of course, eventually, the observer can no longer see it. Over here, you can see now there's no image anymore because logically the observer can't see what's behind him. So to show you that the image isn't there. I don't think it's. Oh, oops! I forgot. The image here is. I forgot I had the line still. My bad. Those aren't. There we go. Now it's gone. I forgot to disable the lines again. Yeah, you can see there's no image of the cube anymore. If I turn around, though, something interesting happens. 180 degrees exactly, or roughly. It doesn't have to be exactly. You can see the cube. Well, if I could turn it just a little more. Okay, I think it was a bit too much. There, that's good. The observer can now see the cube, but from this side. But it looks exactly the same as it would look from this side. Let me like zoom out a bit. Let me like move the observer out a bit more. There we go. Yeah, so now the observer, rather than seeing the red, purple, and black face, is able to see the blue, green, and orange face. Effectively, this simulates opaqueness of objects. Effectively, this is, and this could work for any. This doesn't just work for cubes. Keep in mind, this could work for theoretically any polyhedra. So, like, you can apply the same idea I'm about to show you to it. So some of you are probably wondering, how did I get this to work? So let me draw cube. Alright, so let's say like this is the cube here. Actually, let me exit out of this. Maybe that'll leave. Yeah, sure, just leave. I don't care. Yeah, it helps a little bit. Okay, my eye, somehow my line is less straight with the leg. Without the leg. Did I not draw it? There we go. There's two lines. Okay. Give me a moment. I have to draw this cube. Sorry. I don't want this to take forever, but it is because I have to. It's not going to be a perfect drawing. It's only like a rough sketch, really. So I'm going to create the image like this. Oh shoot, I kind of screwed that one up, didn't I? That's wrong. There we go. I mean, it's close enough. Okay, so we have that, right? There's our cube. I guess, how should we draw this? Oh, oops, I cannot draw. Okay, no. That's not gonna work. Let's just draw a point. There, just like do that. So this right here represents this point right here, right? This represents the observer. Here's the cube. So how I got this to work is by imagining each face. There's 6 faces. Kind of creating a midpoint on the face, like here. They basically calculate the normal vector for the face, so the vector is normal to the face itself. If you know your linear algebra, you could just use the cross product to get this vector. So that's normal. It's a 90-degree angle. This is like such a horrible drawing. Yeah, it's so bad. It's a 90-degree angle with the surface, right? Keep in mind. So what I did is I basically took this point, right? This is the observer. Let's just say the observer is looking this way, looking straight at the cube. Drew another vector from here all the way to here. And I believe this would be the difference between, if I recall, I believe it's the midpoint here, right? So it's this midpoint. Yeah, I don't think I can draw out the equation itself. Yeah. Oh, it's the midpoint here, right? This point here, minus the observer vector point. You subtract them, right? I believe it's like that, and you get this vector that connects the two of them here. Then what you basically just do is you find the dot product between this vector difference and this normal vector, which is a unit vector, and that will give you like the scalar value of this vector projected onto this one. And the idea is that when this vector, like when the dot product between them is 0, that's the moment when like the angle between the face in this vector is also 0, which is the kind of the moment where the space stops being visible to the observer. So the idea is that whenever the dot product is positive, that's when the observer cannot see the face anymore. But whenever it's negative, the observer can see the face. So we basically just apply the same idea to every face on the cube. This. We do it for all the faces, all 6. They all have their own normal vectors. And you just apply this exact same idea to all of them. And the idea is that that'll... I'm not going to bother drawing that. Yeah, I'm just going to draw lines. Of course, this instance with the cube, you don't actually need to do the cross product equation because the three-dimensional axes in three-dimensional space already act as the normal vectors for the faces, because this would be like the xy plane here, or the zy plane, and this would be like the x-axis right here, corresponding to that vector. So it's it's not really, you don't really need to use the cross product for this. For other polyhedra, you'd have to use the cross product. Yeah, it's pretty good because what the ends up seeing, and in this instance would be like, if in other instance it would be like it would look something like this if I could draw it out. So rather than looking like this, I can draw it. Here, I'm trying to draw it out. Hold on, give me a moment. Sorry, it's really slow because of recording it. I wish my computer was better at doing this. It isn't. What the hell? Why did it do that? Really ignore this thing and just look at this, and yeah, you can see like the key would look like this, but except you won't be able to see the back faces here, only just these free faces. All of the other free faces aren't visible. It's math. So effectively we can simulate like opaqueness, yeah, of like an object in 3D space now. I believe this is actually how video games actually simulate this. They use these normal vectors, and they do like a math that's really similar to this, or it's like almost the same. Can't say for certain. Oh, honestly, if you're wondering like how we tell Desmos to make the faces visible or not, we take the sign of this vector here, right? The dot product. Remember, we find the dot product between these two vectors, and then we substitute this into like a function I call the S function, where basically it takes the sign of a value input. It's a real valued function that takes in the sign of an input. Output's either 1 or 0 depending on what the sign is, and if it's basically if it's like 1 or 0, basically output 1 or 0, and then we divide that output, like divide the points that make up the faces by the output like itself, like 1 or 0, and this will make it. I mean, I don't know if you know this, but when you divide by 0 something by 0 in Desmos, it makes it not visible anymore. It stops rendering it. That's how we basically create this rendering effect where the faces like appear individually to each other. So I wanted to show an example of a game I believe is that's doing the math I just showed you. Well, I didn't really show the math yet, but the idea I just showed you involving the normal vector. So this screenshot, I decided to choose Ocarina of Time as an example of this. So in this screenshot, we have Link, the 3DS version, more specific, I guess I should point out, of Link looking at this wall here, and behind him we have the camera, basically looking, of course, right behind at the same wall. In this screenshot, we have Link behind the wall. I used the glitch to get back here, with the camera behind him, and this is actually looking at the same wall, just from the opposite side. So what you notice is that from this angle, right, Link can't see through the wall. He looks straight ahead, but he can't see through it. But from this angle, Link actually he can actually see through just fine. You can even see the opposite wall on the other side. This little like pathway here. So just to show you what this here's like let's say this is the normal vector here. So I believe what's happening is when the camera is looking this way, the normal the vector that's drawn from the camera to this point right here, the dot product between them is negative. So when that happens, it tells the game to make the wall visible. But when it's here, I make another vector. The normal vector would be like right here, roughly. It's going to be drawn from here all the way to here. And when that happens, the dot product will be positive, and this wall will no longer be visible anymore. So I believe that explains what's happening here, why this occurs, why when you look at a wall from one side in the game is told not to display anything, but when you look at it from the side you're intended to look at it from, it's told to display it. And I thought that was kind of interesting. So I wanted to show off the cube a bit more and some of the math, just so you can see what it looks like. First, let me like rotate the cube, so you can see what it looks like in more angles. Let's see how the image changes with respect to the angle of the cube, how what the observer sees. Let me like stop it now though, because it's... There we go. Just keep it there. Oh, this is for the vector here, the purple vector. Yeah, that's the observer direction vector. Here's some of the vectors. That's the observer right there. Here's the functions. This is the S function, right? This right here is the perspective projection itself. This is how the equation for that. This is actually for rotating the cube. It's like a rotation matrix. It's like the final result of it. It's not the actual matrix itself, right? Okay. Cube vertices. It's for the vertices for the cube. That's the lines for the cube. I already showed that before. Faces for the cube. Here's the images for the image of like the cube face themselves. You can see right here there's the S function, and then there's this like this FD1, that's the dot product, like that's being used to detect whenever the faces are supposed to be visible or not. And this is for this right here. I didn't mention this. This is for when like the observer, like when the cube is no longer in the view of the observer, it makes it so the image stops appearing, stops being visible. Okay. Okay, this is just the rest of it for all the other faces. See? Here's the midpoints themselves on the cube, right there. Nothing too unusual with that. And here, oh, and here's the actual equation we're using to detect when face is visible. These faces are here. These are not visible. I believe at least, yeah. So there's a dot product for the faces, and here's the dot product equations for these are for the vertices, but of course they're specific for the face. Well, the vertices for the faces. This is for when the observer this is the detection system for when the observer can no longer see the cube within their view. So they go like in front of the cube, for example, or they look away from it, and this will detect it. This will detect it. It'll no longer display the cube, the image of the cube anymore. And then we have around here. These are the changing the dimensions of the cube. Put this up here. See, now it's not really a cube anymore, it's now like a cuboid. So, and of course this will change the height of it. Of course it's at an angle, so like the values don't really mean what they normally mean, but yeah, it's I think it's pretty much it, honestly. I don't think there's really much else to say. If you're interested in this, you can actually go down in the description, like try this out for yourself if you want. I mean, like, yeah, I always put my work in the description for others to try. Anyway, bye.